Okay, so next presentation is by John Webb on do the laws of nature vary strong gravitational fields with a question mark. And that's going to be answered, I guess.
Good afternoon. This is an observational talk about a new way of searching for new physics, using some, our methods for searching for new physics observationally are limited with astronomical data, but this is one way that I think is promising and is producing some intriguing results. So this is what I want to talk about briefly. I've got too many slides to go through in my 25 minutes, but I will flash through some of them. Forgive me for doing that, but I think it will at least hopefully convince you that we're looking at the details of this fairly carefully, and the results so far are quite intriguing. So, do the laws of nature vary in the presence of strong gravitational fields? One would like to go to a black hole to do things like this. You can't with spectroscopy because there are no spectral features that you can study. Ditto neutron stars, but white dwarfs do offer us an opportunity to make some fairly, actually rather exquisitely precise measurements. And that's what I want to talk about. So there's just a set of mugshots of all but two of the people involved in the project here. A couple of people were sufficiently shy that I couldn't find any photographs of them. An important person here is this guy at the top, Matthew Bainbridge. He's working full-time on the project at Leicester University. Interesting, when I was throwing this slide together and I was searching for a photo for Matthew Bainbridge, Vladimir Putin's picture kept coming up. I have no idea why, but I think I'll have a word with him about that and see what's going on. Maybe there's some message here. Anyway, there's a lot of people involved in the project. People who are experts on white dwarfs. I'm not. People who are experts on some of the atomic physics calculations. People who are experts in measurements with laboratory astrophysics type measurements with Fourier transform spectrometers. People who are experts in calibration issues with Hubble Space Telescope data, and so on. So there's quite a team involved, and well, it's rather fun so far. I'm going to tell you the results first, and then go through some of the details. So this is what we've got so far. We are looking at the spectral features in the photosphere of a white dwarf and looking to see whether there are shifts, relative shifts, I'll explain in a bit more detail in a moment, of these spectral features due to changes in physics, and in particular due to changes in the fine structure constant, E squared over h bar c. We've actually got a reasonable amount of really high quality data. The whole subject, the whole possibility of being able to do this is very new, because it's only about 3 or 4 years ago, 3.5 years ago or so, that it was discovered that in the photospheres of white dwarfs there's a plethora of very weak spectral features, a lot of them being multiplets of iron that we can use for this type of measurement. We've analyzed the data in numerous ways. I'll flash through some of the details of that, but just here are some numbers. So parameterizing a change in the fine structure constant delta alpha over alpha, meaning the value of the fine structure constant in the photosphere of the white dwarf minus the terrestrial value divided by the terrestrial value, we are getting some non-zero results. It's curious. We're down at the precision level of 10 to the minus 5, so for a fractional change in alpha, 4 plus or minus a half times 10 to the minus 5. Nominally significant, and these two numbers come from using different sets of atomic data. But note that I put here plus or minus half, plus or minus question mark, and of course it's this question mark which is the difficult thing, because there are obviously systematics associated with making measurements of this sort. So I'll flash through some of those systematics, not all, but give you at least a flavor of the sort of tests that we're trying to do. Now, we started this project about 3 years ago, 4 years ago, with one particular famous white dwarf. Since then, last year, we've got a whole lot of new data from the Hubble Space Telescope, really good quality spectra, and they also give, and I'll show you these results at the end, towards the end of the talk, give non-zero results. But despite these numbers here, and throughout this talk, I just want you to, I don't want you to go away and think that I'm telling you that this is detection of the fine structure constant in strong gravitational field. I just would rather you think of these things as upper limits on any variation at the moment until the situation gets clearer in terms of understanding all of the error, all of the uncertainties. Well, why do you expect a change in physics near in the presence of a strong gravitational field? Victor Flairbaum's going to give a talk tomorrow. We'll go through a lot of the theoretical details. I will just gloss over that, but just give you a very general reason why it might not be surprising to expect the laws of physics to vary in the presence of a strong gravitational field. And I've kind of summarized that in 4 points here. So gravity is important on large scales because it's an additive quantity. The more particles you've got, the stronger the gravitational force that's created. Scalar fields will naturally couple to gravity, and therefore massive bodies should also couple to or impact on scalar fields. And then the variation in any standard parameters like the fine structure constant can be expressed in terms of variation, and typically are expressed in theories in terms of variations in the scalar fields, with an example there of the dilaton particle in higher dimensional models in string theories. So that maybe you could argue that there's a natural expectation that in strong gravitational fields we might expect variation of fundamental constants. And as I say, Victor will talk, I think, in more detail about that tomorrow. Just a little bit about white dwarfs. The white dwarf is has the gravitational potential at the photosphere of a white dwarf is around about 10 to the 5 times that on Earth. So the physical conditions are quite different. They're relatively bright objects, so that's good because we can get decent quality data with telescopes, albeit in particular only one telescope. We have to observe this in the ultraviolet, so when the Hubble's gone, that's it. This sort of work won't be continued unless somebody puts up another equally good ultraviolet spectrograph in space. And the third reason, well, there are lots of spectral lines, as I've already mentioned, and these spectral lines can be used. The photosphere is a very thin layer around the white dwarf star, only 1 to 10 kilometers thick. So it's a tiny little layer of gas around an object which has a mass not dissimilar to that of the sun, but a radius not dissimilar to that of the Earth. The mass of a white dwarf of the progenitor star was too low to form a neutron star, and you get a white dwarf in a very small number of cases for stars in the galaxies. 97% of the stars in the galaxy. Sorry, a large, I should have said, not small. 97% of the stars in the galaxy will have a mass too small to turn into a neutron star. This is what the spectrum of one well-known white dwarf looks like. These are angstroms, so we're right down the ultraviolet, 1200 angstroms here, 1700 angstroms here. Flux on the y-axis. This is a very strong hydrogen feature that we are not touching in this analysis. And all of these apparently noise spikes here are not noise spikes at all. They're real absorption features in the photosphere, mostly in the photosphere of the white dwarf. And even buried in what appears to be noise here, there are lots and lots of weak lines. It's a very busy spectrum. You can see a little bit more detail on this plot. The lower spectrum here, again, this is right down in the ultraviolet, 980 angstroms, 1020 angstroms over here. All of these features that you see, they're all real features due to a variety of different elements, but there are a lot of iron lines there. And to give you an indication that there's a good understanding of the physics of the photosphere, the top spectrum is actually a synthetic spectrum produced by a stellar atmosphere model for which there's a lot of atomic data input that comes from 2 particular databases. There's a pretty good correspondence. This does not produce a 100% accurate model of the real data, but it's pretty good. And from these stellar atmosphere models, we can We know quite a bit about the temperature in the photosphere, the particle density, and so forth. Zooming in a little bit more, just to show you the lines that we're using to measure the fine structure constant. This is what they look like. They are very weak, but nevertheless clearly and significantly, some of them are stronger obviously, present in the spectrum. It's a question of there being a lot of work beforehand to identify the species that you're looking at in the photosphere to be able to talk about shifts due to a change in the fine structure constant, which can be parameterized by looking at a small change in the frequency of a given atomic transition with respect to the fine structure constant, dx here parameterized actually in this way, alpha in the photosphere over alpha naught squared minus 1, relating that to Q, a sensitivity coefficient. The interesting thing about this is that the different atomic transitions in the spectrum will shift by different amounts and in different directions because the sensitivity coefficient is determined by the atomic characteristics of the multiplet that you're dealing with. There's quite a lot of detailed atomic physics in that, which again I think Victor may mention in his talk tomorrow. So again, looking at wavelength, just a short section of a spectrum, synthetic, just to illustrate a point, 1361 to 1366 angstroms. On the y-axis here we have a change in the fine structure constant, so this is just a synthetic spectrum. Some transitions have bigger Q coefficients, bigger Q values will shift more strongly for a given fractional change in the fine structure constant, and others are less sensitive and won't change as much. This is really good because it gives us a unique pattern of shifts for many lines which we can then model to provide a constraint on the fine structure constant. The first paper on this subject appeared here in 2013. There have been a few other papers which I list on the last slide of the talk, and there's quite a few papers in preparation. The one that's been studied in detail is one particular white dwarf. It's called G191-B2b, and there's a set of parameters about this. For those of you who know anything about spectroscopy, this is the spectral resolution, 144,000. This is really good, and we can study the spectrum. We can study the profiles of individual lines in the spectrum in great detail. 140, just to give a comparison, compared to some of you may know a little bit about the quasar analyses that we've been doing to look at for high redshift temporal or spatial variations in the fine structure constant. That is good data and comes from the VLT or from Keck. Very high quality data, but the spectral resolution is only about 40,000 compared to this, 144,000. So this is really nice data. And of course, what we do then is we compare the observed wavelengths of transitions in the photosphere with laboratory wavelengths, hoping that we're doing the correct identification of all the lines in all cases. And then we parameterize a change in alpha in terms of, here we go, alpha r minus alpha naught, alpha r just being the value at the photosphere of the white dwarf, in terms of sensitivity coefficients, relating those to the gravitational potential in the white dwarf photosphere. So, without going through this in too much detail, you can easily produce a relationship between the fractional change, the fractional shift in a wavelength, as a function of the fractional change in the fine structure constant, sensitivity coefficient, and Z. Shifts, of course, in the stellar spectrum will arise due to a number of reasons. There will be, of course, the peculiar velocity of the star, but that velocity applies to all the lines in the spectrum equally. Gravitational redshift, ditto. Change in the fine structure constant, different. Those will be treated differently, though the fine structure constant will shift the individual lines in different ways. These are the early results. If you plot as a function of the sensitivity coefficient that I showed you earlier, a fractional change in the wavelength, and you split into two colors here, two different species. I've mentioned only iron so far, but there are also a lot of nickel transitions. You find something really strange, because the previous relationship I put on the last slide expects you, when plotting delta lambda over lambda against the sensitivity coefficient Q, that you have a straight line. Indeed you do, but you have two different straight lines. The slope of this, by the way, gives you delta alpha over alpha, the slope of these curves, but you have two different slopes for two different species. Well, that doesn't make any sense whatsoever. There's obviously something wrong here. Not quite sure what that is, but almost certainly it has to do with the laboratory wavelengths. We looked in enormous detail at laboratory wavelengths, and since these measurements were done, which were 2013, two experiments have been carried out, one in Paris and one at NIST in Boulder, Colorado, to remeasure all of the laboratory wavelengths for several species, but in particular iron, and I'll show you the newer results shortly. Or maybe not. Something's gone wrong. Okay, everything went yellow. Never mind. I don't know what happened there. Anyway, so actually, that's better, isn't it? Okay, so from that previous graph, if you actually take the slopes, of course, one was positive, one was negative. So you do indeed get different. You get different values. Something is clearly wrong with the results. So basically, we went away and did it all again in much greater detail. So let me skip a few things, but just summarize the atomic data. In the first paper that appeared from Beringet and collaborators in 2013, we used laboratory wavelengths, which were the best available, from 1975. Those wavelengths have been recalibrated. That 1975 data has been recalibrated in a paper in 2014. And nominally, the laboratory wavelengths are very accurate. And interestingly, the two new experiments that have been done in Paris and Boulder have only marginally improved on 4 milliangstrom wavelength uncertainties, although it looks like there are systematics in the wavelengths. That's why I said you have to treat these values as upper limits for the time being. I'll just run through four tests for systematics that we've done very, very quickly. One is to assume that laboratory wavelengths that have been measured have random errors on them. And then what we do is essentially a sort of bootstrap method where we randomize further the laboratory wavelengths and then measure continuously in different runs of the experiment the value of alpha to see how much additional uncertainty we have to plonk on top of the laboratory wavelengths to increase the measurement error on alpha by a given amount. So we did 1,000 numerical experiments where we then look at the distribution of alpha and also chi-squared for the fit to the data to see at what point we begin to violate the data. This gives us some kind of handle on how good the laboratory wavelengths are. That's one test. I can't go through all these numbers in too much detail, other than to tell you it looks like, interestingly, by doing this, probably the uncertainties are as good as 2 milliangstroms on the data, and however, unfortunately, that does translate to an uncertainty of order 10 to the minus 5 on delta alpha over alpha. So it would be just fantastic to find a laboratory experiment which could really measure these things accurately. We're measuring atomic lines in the photosphere of a white dwarf with better accuracy than can be measured on a Fourier transform spectrometer on Earth, which is kind of actually annoying. It would be nice to have it the other way around. Another test is spectrograph is an instrument that obviously has uncertainties associated with it, and you have to ultimately collect your data onto a detector, and you have to calibrate your spectrum in terms of wavelength before you can start measuring anything, and there are uncertainties in that procedure. And so you need to really understand what the uncertainties in that procedure are. So again, I won't go into too many details other than to say you can assume different types of models for a distortion pattern in a spectrograph, apply that model, that distortion model, with the free parameters describing that distortion model to the data, and then see what happens to the chi-squared of the fit to the data. And that's basically, this is chi-squared as a function of the parameter which describes the distortion in the simple model. And then you can actually, just by using the normal technique of minimum chi-squared plus 1 or 4 for your 1 or 2 sigma uncertainties, quantify how much a distortion on the spectrograph would translate into an uncertainty on alpha. In this particular case, it's interesting. For this first white dwarf that we looked at, it's rather interesting because there is an insignificant shift away from 0, but it's there, but it's not a significant shift in terms of the parameter for distortion. In other words, there's no statistical evidence for distortion in the Hubble Space Telescope spectrograph that we use, which is, by the way, exactly what all the experts who work on the instrumentation would have predicted and did predict, but we wanted to check it. But if nevertheless, of course, you do measure a non-zero distortion. If you apply it, the answer alpha actually moves further away from 0. So there's a reason for being cautious and perhaps not applying it in that case. We're using a third test. We're using iron to make these measurements. Iron, of course, has isotopes. When you create a synthetic spectrum of iron like this, you then have to assume an isotopic abundances, and the only ones we know of are terrestrial. We don't know what the isotopic abundances of iron are in astrophysical sites, so you can experiment with that, play around with the isotopic abundances, and see what that does to alpha. It doesn't do anything significant, is the bottom line. Last test I'll just quickly go through. Calculating these sensitivity coefficients is an interesting process, and it's not always clear that you can correctly associate a given sensitivity with the appropriate iron multiplet in the spectrum. It's a complicated business, and so there is some uncertainty involved in that, but one can carry out tests to randomly reassign sensitivity coefficients to different transitions and look at what impact that has on the measurement of alpha. This turns out to be, interestingly and thankfully, a very small effect. I'm going to skip 2 tests because I'm running out of time, and I want to show you just show you the results. This is the interesting bit. So on the x-axis here, I've got surface gravity, little g, in centimeters per second squared. This is the acceleration at the surface of the white dwarf, and this is a fractional change in alpha in units of 10 to the minus 6. 0 is here, and all of these different points are the new Hubble Space Telescope observations. The one that was studied initially is this one, G191 minus B2b. Now we have these other measurements, and they scatter a bit. Some of them, as you can see, are inconsistent with 0. If you want to pick out by eye the ones which have the smaller error bars, well, there's one down here with a smaller value of surface gravity, and maybe the ones with small error bars at higher values of little g give a larger, more positive value of delta alpha over alpha. But it's just a hint in the data, really. This just illustrates the impact of tests. I didn't go through 2 of them. What those tests do to delta alpha over alpha. They do shift the data. I'm almost done. But but don't seem to explain what we actually see. We've looked at the Zeeman effect for magnetic field splitting of the lines, Stark shift, long-range distortion I mentioned. This is a summary of the new results. But now, looking for one white dwarf, G191, and actually we have 4 sets of wavelengths, set 1, set 2, set 3, set 4, delta alpha over alpha. This, I don't know if you can read this, this is 0, 1, 2, 3, 4. So even no matter which set of wavelengths you use, we don't make that, even though I think wavelengths are a problem, we don't make this go to 0, intriguingly. There are systematic problems in the wavelengths that are concerning, nevertheless, and I'm going to just, in order to finish up on almost on time, just show my penultimate slide. So just to summarize, there are apparent non-zero results from several white dwarf photospheres. I would not say that we have properly fully understood yet all the potential systematics. I really do think that we are getting on top of them and that we can get on top of them, but there's more work to be done. I'll just explain that very briefly on the last slide. We're closing in on a good understanding of the systematics. Laboratory wavelengths are indeed a difficulty, but we do have these new experiments from NIST and Paris. And one thing I didn't mention is that we can get rid of almost all the systematics by not trying to measure an absolute value of delta alpha over alpha, but looking at delta alpha over alpha. That is the measurement of alpha in one white dwarf with respect to another white dwarf. That will remove most of the systematics. And the 2 slides ago, I basically showed you that, where there are indeed differences between nominally statistically significant differences between different white dwarfs. There's some recent papers listed at the bottom. Anybody's welcome to these slides. And my last slide, just to say work in progress. Right now, we're trying to properly model magnetic fields. Probably magnetic fields are not important in the white dwarfs that we are looking at, but nevertheless, if there is a white dwarf, then the orientation of the white dwarf spin with respect to the line of sight to Earth is going to be important. Because if you were looking down at the pole of a white dwarf with a magnetic field, you will measure there will be a different apparent magnetic field than if you're looking at the equator. That means the Zeeman splitting will be different as a function of position on the white dwarf surface. We only see a point source when we look at the white dwarf, so we have to carry out a rather ugly integral over the surface of the white dwarf to properly understand the profile shapes that need to be fitted to the data in order to make these measurements. That was a rather complicated technical point. I apologize, but at least maybe you get a sense for it. We are also using artificial intelligence methods for fitting the spectra automatically to remove any possible human bias. There are papers, the paper on that was listed on the previous slide. I would love to get my hand on more laboratory wavelengths, but I think I'm a little bit like this dog here dreaming of this delicious bone. I don't think it's going to happen because it's just too hard for the experimental people to do, and it's very expensive. And I will stop there. Thank you very much.
Okay, time for questions or comments. There's the microphone over there.
Thank you. Now it's a kind of I don't know, kind of trivial type of questions, I'm sorry, but still, you have this influence of gravitational field, right? What is theoretical estimate how gravitational field would influence the spectra by itself without delta alpha over alpha?
Oh, you mean what's the gravitational redshift of the, how much do the lines shift by? Yeah. Well, a lot, about, I mean, the unit that we use is in kilometers per second. I don't remember the exact number, but it's of order 30 kilometers per second.
Yeah. So in this way, you accuracy enough to see the gravitational shift as well?
Yeah, it's just a free parameter in the fit. That's easy, yeah, yeah.
So may I add a comment to this? In ratio of frequencies, gravitation should disappear. This is the main idea.
Yeah.
We always measure ratio of frequencies.
Disappear completely or in the
No, but in ratio of frequencies, in general relativity, redshift disappear.
It is exact statement?
Exact statement. So all you see is deviation from a general relativity.
So maybe I can ask you. So the expected shift from gravity, is it that magnitude? Is that what they claim?
Yeah, but the point is that all lines are shifted by the gravitational redshift by precisely the same amount. So it's an irrelevant parameter. So it's a nuisance parameter. And we can solve for that exactly. So it doesn't, the uncertainties that I showed take that into account. Yeah, there was a question at the back there. Okay.
Yeah, so you whetted our appetite at the start with this discrepancy between nickel and iron, and so you didn't show nickel again.
No, haven't done
That's
nickel.
not reconciled yet.
Well, no, but nothing has been done. We've focused completely on iron because there are more transitions and because the wavelength uncertainties for the laboratory data for iron are better. So I'm basically, psychologically, I'm just discarding nickel. Yeah.
Okay. Oh, there's one more.
Just wonder if you can do the other way, assuming the constant is a constant, and you use your observation to calibrate the wavelength in the laboratory. That's what we do with pulsar timing.
I don't want anything to do with that. you could do, but what would you gain?
You help determine the laboratory measurement.
Well, what's the point in having the wavelengths in the first place?
I don't know.
Neither do I.
Okay, so I see no further questions. Let's thank the speaker again.